Hello everybody. This video is an introduction to decimals. Before I get to decimals though, I want to discuss briefly why decimals are important. We have been discussing fractions during the last 4 videos. Fractions allow us to represent a portion of a whole unit, so we can talk about half of a pizza or 2/3 of a pizza. Specifically, what we have been studying are called common fractions, that is, fractions written with an integer for both the numerator and denominator. Common fractions are still widely used, but they are problematic in some ways. For one thing, it is sometimes difficult to compare the magnitudes of two fractions. For instance, which fraction is greater, 5/9 or 6/11? It is also sometimes difficult and time-consuming to add and subtract fractions. For instance, what is 4/21 plus 6/35? The difficulty in both cases is in working with fractions that have different denominators. To solve both problems that I presented, it is necessary to find a common denominator and then convert the fractions into equivalent fractions using that common denominator. What if we used a set of fractions where the denominators are either the same or are quite easy to express as common denominators? That would greatly simplify comparisons and arithmetic operations between fractions. This is where decimals come in. Decimals are an alternative system for expressing fractional portions of a whole. The concept of decimals has been around for a long time, but the modern use of decimals has only been around for about 400 years. Decimals greatly simplify both the problem of comparing the magnitudes of two fractions and the problem of adding and subtracting fractions. We will learn, though, that decimals have their own limitations. So, what is a decimal? Let's take a small step back first. We have 10 digits in arithmetic, 0 through 9. We can express any integer that we want by a combination of these 10 digits. When I write a number like this, then our common understanding of that number is based on both the position and magnitude of the digits that make up that number. We would explain that the rightmost digit occupies the ones or units place, the digit immediately to the left occupies the tens place, and the digit to the left of that occupies the hundreds place. So the notation I've shown means that our number has 5 hundreds, 3 tens, and 5 ones, 535. There are 2 5s in this number, but they don't mean the same thing by virtue of their position. I can continue to add digits to the left in order to make larger and larger numbers. Each position I add to the left represents another power of 10. I can express any integer, no matter how large, in this manner. We are so used to this that it is second nature to us. In fact, we can make the numbers so large that, for most of us, myself included, we don't know how to pronounce the number, but it is still easy for us to determine its size relative to other numbers and to use it in mathematical operations. What happens if we want to talk about numbers that are smaller than 1, that is, fractions? Well, we can simply add numbers to the right of the ones place. First, we use a decimal point to annotate where the ones place is. Now, using the same convention as before, every place to the right of the decimal point is 1/10 of the value of the place to its left. That is, the first place to the right of the decimal is the 10th place, the place to the right of that is the 100th place, and the place to the right of that is the 1000th place. I can continue adding digits to the right for as long as I want. Each place will be 10 times smaller than the one to the left of it. Decimals are simply another way to express fractions. If I have a number like 2.3, then this number has 2 in the ones place and 3 in the 10ths place. This number is equivalent to the mixed fraction 2 and 3/10. 5.27 is equivalent to the mixed fraction 5 and 27/100. Can you give me the fractional equivalent of 2.351? The 1 occupies the thousandths place. This gives me the denominator of the equivalent common fraction. The answer is 2, and 351 over 1,000. One more example. What is the fractional equivalent for the decimal 0.1234? Remember that the first digit after the decimal is the tenths place, the next is the hundredths place, the next is the thousandth place, and the next is the 10,000th place. 4 digits to the right of the decimal gives us a denominator of 10,000. The answer is 1,234 over 10,000. Before we go any further, there is one more thing I want to talk about. For some mathematical operations on decimals, which we will see shortly, I want to change the number of decimal places in a number without changing the value of that number. For instance, I want to be able to convert the decimal 0.2 to the equivalent decimal of 0.200. But we can't just do what we want in arithmetic unless we prove that it is in accordance with the specific set of rules or laws which govern arithmetic. So I must prove that 0.2 is equal to 0.200. Let me do that right now. 0.2 is equal to 2 over 10. 0.20 is equal to 20 over 100. 0.200 is equal to 200 over 1,000. When we go from 2 over 10 to 20 over 100, we are multiplying both the numerator and denominator by 10. That is, I am multiplying the original fraction of 2 over 10 by 10 over 10. But 10 over 10 is simply equal to 1. 1 is the multiplicative identity, which means that we can multiply any number by 1 without changing that number. Our justification is an application of the rule of the multiplicative identity. Every time I add a 0 at the end of a decimal, I am effectively multiplying the number by 10 over 10, that is, a number equal to 1. I can add as many zeros to the end of the decimal as I want without changing the value of the decimal. Let's apply that idea in comparing the magnitude of decimals. Suppose we want to compare the magnitudes of the following two decimals, 0.2 and 0.195. What would we do? Well, we use the same approach that we would for common fractions, but it is much easier with decimals. For common fractions, we find the common denominator, express both fractions using that common denominator, and then compare the numerators. The decimal equivalent of that is expressing both numbers as decimals with the same number of places to the right of the decimal point, and then comparing the two decimals. 0.2 has 1 place to the right of the decimal point, and 0.195 has 3. So we express 0.2 as an equivalent decimal with 3 places to the right of the decimal point by simply adding zeros to take up the additional places. Now the decimals we are comparing are 0.200 and 0.195. 0.200 is the larger number since 200 is greater than 195. Addition and subtraction of decimals are similarly straightforward. Both are done in a manner similar to the addition and subtraction of integers. Let's try an addition example. What is 0.54 plus 0.3? First, express both numbers as decimals with 2 places to the right of the decimal point. We have 0.54 plus 0.30. Then do a column-by-column addition of the numbers starting from the right. 0 plus 4 is 4. 5 plus 3 is 8. The answer is 0.84. Let's try another one that is just a little bit harder. After I give you the problem, then pause the video while you try to work it out. When you're done, resume the video. What is 1.591 plus 0.73? Please pause the video. Let's go through this problem. First, notice that we have 3 places to the right of the decimal point in the first number. For the second number, we have only 2. Let's write the second number with 3 decimal places. We do that by simply adding a 0 onto the end of the number. Our math problem is now 1.591 plus 0.730. Next, do column by column addition starting on the right. 1 plus 0 is 1. 9 plus 3 is 12. Write the 2 and carry the 1. 1 plus 5 plus 7 is 13. Write the 3 and carry the 1. 1 plus 1 plus 0 is 2. The answer is 2.321. How did you do?
I'm learning so much.
Great. Let's try a subtraction problem. What is 1.56 minus 1.8? Notice that the first number has 2 places to the right of the decimal point, and the second number only has 1. So first, we must add a 0 to the second number. Our problem is now 1.56 minus 1.80. Now recall that subtracting a number is equivalent to adding a number of the same magnitude but opposite direction. So my problem is now 1.56 plus negative 1.80. Since the signs are opposite, we subtract the magnitudes and take the sign of the number with the largest magnitude. 1.80 minus 1.56 equals 0.24. Since the sign of the number with the largest magnitude is negative, the answer is negative 0.24. We're done. Let's try one more. After I give you the problem, please pause the video and try to work it out yourself. Then resume the video once you have the answer. What is 2.3 minus 1.765? Please pause the video. Okay, let's figure this out. First, we must add 2 more decimal places to the first number so that both numbers each have 3 places to the right of the decimal point. Our problem is now 2.300 minus 1.765. Since both numbers are positive and the magnitude of the first number is larger than the second, our answer will be positive. You can convert this to an equivalent addition problem if you like, or you can just do the subtraction in a straightforward column-by-column manner. Either way is acceptable. You end up with the same number. Let's use the latter method for this problem. I can't subtract 5 from 0, so I have to borrow from the left. But 0 is to the left, so I have to go 1 digit further left to the 3. 3 becomes a 2. The 0 in the second decimal place becomes a 10. Now reduce that 10 to 9 and send 10 over to the 0 in the third decimal place. 10 minus 5 is 5. 9 minus 6 is 3. Reduce the 2 in the ones place and send 10 over to the first decimal place. 12 minus 7 is 5. 1 minus 1 is 0. The answer is positive 0.535. I think we've taken a big enough bite of the apple for now. In the next lesson, we'll talk about...
That's really quite remarkable. That just happens to be the first line of my new aria.
I knew I wouldn't make it through a lesson without an interruption. Excuse me, who is this?
Why, I'm Ursula, the Decimal Diva, of course. Do you have a math book you would like me to autograph?
No, thank you.
My aria is entitled The Decimal Point of Love. I will be performing on Friday evening at the Met with Bocelli.
Wow, I'm tremendously impressed. Bocelli at the Met? What time is the performance?
As soon as he gets off work.
You're telling me that you're performing an aria with Andrea Bocelli, but you have to wait until he's done working?
Not Andrea Bocelli, silly. He is so yesterday. I'm performing with Bobo Bocelli. He's Andrea's third cousin twice removed. He's the next great undiscovered talent.
But you're performing at the Metropolitan Opera in New York City?
Most decidedly not. 2 stuffed shirts for Bobo and me. We will be gracing the Metropolitan Bar and Grill in beautiful downtown Sheboygan. Do listen to my aria. Just give me a brief moment to warm up. La 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 la. So, me.
No, thank you. I have to get back to business.
Well then, toodaloo, darling.
Oh, yeah, toodaloo. That was confusing. As I was saying, we have taken a big enough bite. Well, we've done enough math for now. Let's continue with multiplication and division of decimals in the next lesson. In the meantime, sit back and enjoy yourself. Maybe listen to an aria or two. Have a good day, everyone.
you at Veterans Upward Bound very soon and recommend a friend.